We studied orientation of vector bundles, and now we want to extract some geometric consequences of orientability. In order to do so, on top of orientability, we are going to consider some of the order results that already appeared in the course, as for instance, density of C-infinity maps in the set of continuous maps, or the fact that transversality is an open and dense property. The first result that we are going to consider is that a one-dimensional orientable vector bundle is always trivial, right? Let us consider a one-dimensional oriented vector bundle, okay? In this case, we can consider an atlas, okay? An atlas of vector bundle, of oriented vector bundle. And this means that this map phi ix, which is an isomorphism from the fiber at x and the line, because we are considering a one-dimensional vector bundle, okay, this map over here preserves orientation. For every x that belongs to ui and for every index, okay? We consider oriented vector bundle charts. Okay, what we want now is using this property in order to construct, to build a vector bundle chart of psi whose domain of definition is the whole M. In that way, we get that our vector bundle is trivial. But let's actually realize something, is that if U belongs to the fiber of X and it's not the zero vector, we get that these maps over here, the phi ix, are always positive in U or always negative. This could be whenever X belongs to UI, or we have that they're always negative. And why is that? Because if U actually, if the set consisting just of U is a base of the fiber EX. If that base is positively oriented, then since this isomorphism preserves orientation, the image has to be always positive. And if the base whose unique element is U is negative for the orientation of our vector bundle, then it has to be sent to a base of R that is negative, so a negative number. So we get this property for every X that belongs to some UI, okay? This is gonna be very important in order to build this trivialization of psi. And how is that? Because now we consider UI, which is just UI is an open cover of our manifold M, and we can consider a partition of unity subordinated to this open cover. Okay, partition of unity subordinated to the open cover. So this means, sorry, in particular, that the support of theta I is contained in UI. Now, we are going to define our chart psi m. The chart has to be defined in the whole manifold. And so we have to define an isomorphism psi x for every x in M between the fiber EX and R. And this isomorphism is going to be the sum for all indexes of theta I at the point X times phi IX. Okay, in the neighborhood of X, this is a finite sum because the family of supports is locally finite. And what we get at every point is a linear combination of linear transformations. So a linear transformation. But obviously the problem here is that we need to show, it's clear that it depends continuously on X, that's not going to be an issue, but we need to show that it is actually an isomorphism. So let's consider a vector U in the fiber such that this property is satisfied. Okay, we can do that. If we consider U such that we have that, we replace U with minus U. And what happens for that U that belongs to our fiber and is not the zero vector is that when we consider psi of x applied to U, this is just the sum of theta ix times phi ix of U. And what happens is that all these values over here are positive and all the values over here are greater or equal than 0, so this is greater or equal than 0. But it's better than that. There is one I, at least, such that theta I of x is positive. If we fix x, theta I of x is positive. In this case, x belongs to the support of theta I. That means that x belongs to ui. That means that this expression is positive, and we have here the product of two positive numbers. So it's the sum of non-negative numbers such that at least one of them is positive, so the sum is positive. But this implies that psi of x is not the zero map, and since psi of x is a linear map between two vector spaces of dimension 1, then psi of x is necessarily an isomorphism, right? It's a linear isomorphism for every x in M. And that's it. We get our vector bundle chart. And as a consequence, okay, then psi M is a vector bundle chart. And as a consequence, we get that our orientable vector bundle is indeed isomorphic to the trivial bundle, as we wanted to show. Okay, let us see now that when we consider a manifold with a non-empty boundary, then the algebraic normal bundle of the boundary in M is indeed orientable. And as a consequence of the previous result, then trivial. Okay, what we have is that the tangent space of the boundary of M is included in the tangent space of N restricted to the boundary, and then we have this map to the normal bundle, and this short exact sequence is indeed exact. Okay. Okay, since this vector bundle has dimension M, if M is the dimension of our manifold, and this one has dimension M-1, the last one has dimension 1. So the normal bundle is a one-dimensional manifold. But what we have is that if we consider the local situation, we can actually choose a chart for our manifold, okay, in which we have that the boundary of M is given by the vanishing of one of the coordinates, for instance, the first one. So we're in a situation more or less like the one that is in the picture. And what happens now is that we can choose an oriented base in a continuous way for the normal bundle in every point in the boundary. What we have to do is actually considering here a vector, a tangent vector that is transverse to the tangent space of the boundary and that points towards the interior of M. And the class of such a tangent vector in the normal bundle is indeed a base. It's an oriented base, and this construction defines a unique class of bases. So it defines an orientation of the normal bundle. And that's the proof, okay? The algebraic normal bundle is orientable, and since we saw that every one-dimensional vector bundle that is orientable is trivial, then the algebraic normal bundle of the boundary of M in M is trivial. Let us consider a consequence of the previous result. Let M be a connected manifold, and let M be a closed connected submanifold of N of codimension 1. Let us assume that both manifolds have no boundary. Okay, assume that M separates N. Okay, this condition is by definition that N minus M is not connected. Okay. Oh, is not connected. So with this hypothesis, the normal bundle of M in N is trivial. N minus M has two connected components, and the boundary of these connected components is equal to M. Okay, so let's see if how we can prove this. We consider our manifold M, which is a submanifold of N, and locally we can see this manifold in some local chart as the vanishing of one of the coordinates. So we can consider something like this. And if, for instance, that coordinate is x1, there are two sides. X1 positive, okay, and x1 negative. And what we want to say is that this construction already implies that since locally we have two connected components, when we consider a set like this minus M, then if N separates N, the plus and the minus have to be in different components of the complement of M. Why is that? Let C be a connected component of N minus M. Okay, then there exists a point in the frontier of C. Okay, there exists C is not the whole manifold N, so there exists the set closure of C minus C is non-empty. And in particular, that point that is in the frontier of C has to be a point of M, okay? This is a subset of M. So you have points of this connected component always very close to M. But if we have a point that is very, very close to M, since M is also connected, we can follow here M and enter here. So the connected component C is either the same component, the same connected component as the connected component of the points with a plus, labeled plus, or is the connected component of the points labeled minus. In particular, that means that the pluses and the minus are in different connected components, because if they are in the same, then essentially uh, every connected component of n minus m is going to be, yeah, the connected component of the union of these two sets, and that's it. So the pluses and the minus are in different connected components, right? And we can do the construction, the same construction in every point of M, right? If we do this here, locally, we are going to have that M separates this, let's call it red box over here. But if we consider points over here and we follow M, we are going to end here or here. So this one of the sides is going to be a plus, and the other one, since they cannot be in the same connected component, because of the same argument that we use here, has to be a minus. So that implies, by doing this construction at every point, that the boundary, the frontier of C, actually, has to be equal to M, and that in a neighborhood of M, C is indeed the union of all these regions labeled with a plus, or the union of all these regions labeled with a minus. In particular, what we get is that the closure of C is a manifold with boundary. And this boundary is M. Okay, so we have a manifold with boundary, and in particular, now what you can realize is that the normal bundle of the boundary of the closure of C, the normal bundle of the boundary of the closure of C, that is M, is orientable. But that normal bundle is the normal bundle of M in N. So we get that this normal bundle of M in N is orientable, and since it has dimension 1, because M has codimension 1, orientable of dimension 1 implies trivial. We get the last property too. Every connected component satisfies that the frontier of the boundary of this connected component is the whole M, and we saw that indeed we have two connected components. Yeah, because every connected component is in the connected component of the points here labeled with plus, or the points labeled with minus. So at most we have two connected components, and indeed we have two, one for the pluses and one for the minuses. Okay. Now let us consider the following corollary of the previous result. Then let M be a simply connected manifold, and let M be a close connected submanifold of N of codimension 1. Let us assume that these manifolds are without boundary and that M separates N. Then M is orientable. Okay, what we have is that there exists this short exact sequence. Okay. And now what our goal is proving that this vector bundle over here is orientable, right? But the first thing that we can realize is that as a consequence of the previous result, and since M separates N, the normal bundle of M in N is orientable and then trivial, but in particular orientable. Okay, so this manifold, this vector bundle over here is orientable. We have another interesting property too, is that n is simply connected. But every vector bundle over a simply connected manifold is always orientable. So that implies that the tangent vector bundle of n is orientable. But the restriction of this vector bundle to a submanifold is going to be also orientable. So but now we have a short stack sequence of morphisms of vector bundles, and two of the vector bundles in the short stack sequence are orientable. Then the third one is also orientable. So as a consequence, the tangent space of M is orientable. But by definition, that implies that M is orientable. Okay, so it's just a simple consequence of the previous result and the properties of short stack sequences of morphisms of vector bundles. We already saw that it is interesting to know whether a submanifold of codimension 1 separates the ambient space. Here, we are going to see that under certain conditions, n separates n. The submanifold of codimension 1 separates n. Indeed, we consider n a simply connected manifold, and M is going to be a compact connected submanifold of n of codimension 1. Both these manifolds have no boundary, and so under this hypothesis, M separates n. So what we are going to see is the following. We are going to consider x0 and x1 points that belong to n, but do not belong to M, okay? And now we are going to consider a map from the closed interval 0, 1, a infinity map, to n, such that the initial point is x0 and the final point is x1. Okay. And we want to associate to this map some invariant. So in these conditions, there exists gamma hat a infinity path that is homotopic to gamma relative to 0, 1, and such that gamma hat is transversal to M, right? This is not difficult to prove, okay? It's essentially what we are doing over here is saying that it's using that transversality is an open and dense property. It's true that we need to fix the values at 0 and 1, but that's not difficult at all. In that situation, what we are going to define is an invariant, okay, which is just the number of points in the preimage of M. Since we have transversality, this preimage is a compact subset of dimension 0, so a finite number of points. So this number is well defined, and we are going to define this number modulo 2. So it's going to be an element of the group of integers modulo 2. It's, what we are interested in is whether or not this number is even, okay? Very good. So we are in this situation. This is going to be very useful to prove that M separates N. What we want now is the following. If we have two maps alpha, two paths, sorry, that are, say, infinity and And okay. And that are homotopic relative to 0, 1. Okay, and the initial point for both of them is x0, and the final point for both of them is x1. What we want to show is that the values associated to alpha and beta are the same. Okay, that's our goal. Okay, that's going to be very, very useful in the proof. So what happens here is that we can suppose that alpha and beta are transversal to n. Okay, so we can suppose that alpha and beta are transversal to n. That's because we can replace alpha with alpha hat and beta with beta hat. Okay, since alpha hat is going to be homotopic to alpha relative to 0, 1, and homotopy is an equivalence relation, that's possible. Okay, it's just replacing, if necessary, alpha with alpha hat and beta with beta hat. So we can suppose this. Okay, we can consider now the homotopy between these two paths, right? And this homotopy is going to be a map, a continuous map from the square 0, 1 square to n, okay, such that f of s0 is alpha s, f of s1 is beta s, f of 0t is x0, and f of 1t is x1 for every s and every t. That's the situation we are. We can even suppose a little bit more without lack of generality. Okay, here we have our square. Here we have alpha. Here we have beta. Here we have x0. Here we have x1. Okay, and we can suppose that f is f is C infinity in the neighborhood of the inferior side and the side on top. Okay, in the neighborhood of okay, 0, 1 times 0 union with 0, 1 times 1. So this 2 1. That's not difficult. That's because we can put here, okay, something that we could do is defining an homotopy G, for instance, in in 0, 1 times minus 1, 2, okay, with values in M, and the image of ST is going to be f of ST if t belongs to 0, 1. The image of ST is going to be alpha of S if t is smaller than 0, and the image of ST is going to be beta of S if t is greater than 1, right? So indeed what we are doing here is doing something like that and considering here copies of alpha and here copies of beta. The advantage of doing this is that now in the neighborhood of the side on top and this other inferior side, since the map is equal to alpha or to beta, is infinity. And then we can reparameterize so it's a square again. So we can suppose that. Yeah, okay, f is infinity on the neighborhood of these two sides. Okay, the downside and the upside. Very good. But now, since alpha is transversal to n, we're going to have a neighborhood here of this downside and a neighborhood of the upside in which the map f is actually C infinity and transverse to n, right? It's infinity because we already saw that it's infinity in the neighborhood of these sides, and transverse because it's transverse on alpha and beta, and transversality is an open property. So yeah, we have these two properties. And so what we can do is modulo a small perturbation by using that transversality is an open and dense property. We have that there exists a C infinity mod p, okay, such that G is equal to F in the neighborhood of the down and the upsides. That can be actually checked out. The idea is that since there we have the property that we already need, the property that we need, we don't have to change anything. So all the proofs till this point is just to say that we can assume that G is indeed C infinity and transverse to n, right? It's just that. Now we consider the preimage of M. M is a codimension 1 manifold, codimension 1 submanifold of M. So the preimage of M, now what we have is that because of transversality, this is going to be a neat submanifold of the square of codimension 1 or of dimension 1 because the dimension of the ambient space being the square is 2. So when we design here this preimage, we make the picture, it's going to be something like this. Okay, we are going to have some arcs going from one side to the other. We could have even things like this. If we have one of the connected components of this manifold that intersects the boundary, then it intersects the boundary twice. It can be twice in one side or once in one side and once in the other side. And we can have components that don't intersect the boundary, okay? We cannot intersect the boundary here or here because the image of those points is x0 and x1, and those points don't belong to M. So as a consequence of this construction, the number of points that we have in the upside or the downside is not necessarily the same, but they have the same parity. Here we have 3 and here we have 5. So as a consequence, we deduce that lambda of, L of alpha x0, x1 is equal, to L of beta x0, x1. Okay. And now we can go with the proof. Now assume that now consider here the boundary of M, and we can choose 2 points, x0 and x1, very close to the boundary, but locally each one of them is in one of the sides. So in this way we can actually consider a C infinity path going from x0 to x1 and intersecting the boundary of M once transversally. That implies that if this path is gamma, the invariant of gamma x0, x1 is going to be the class of 1, okay? But we say that this implies necessarily that x0 and x1 are indifferent connected components of the complement of M, okay? That's our claim. We claim that x0 and x1 are indifferent connected components of n minus m. Suppose that's not the case. Okay. Otherwise, there exists a map path alpha from 0, 1 to n minus m, such that the initial point is x0 and the final point is x1. And we can perturb this map slightly so that it is infinity and that it still does not intersect the boundary of M. Okay, so there exists alpha hat that belongs, sorry, that whose image is contained in the complement of M, and such alpha hat is homotopic to alpha relative to 0, 1. Okay, now what we have is obviously the intersection with M is transversal because it does not intersect M. And what we get is that L of alpha hat x0, x1 is equal to 0. But that's going to provide a contradiction because now we are going to use finally that n is simply connected. We have gamma, which is a path in n such that gamma 0 is equal to x0 and gamma 1 is equal to x1. And we have a path alpha hat also in n that satisfies that the initial and final points are the same. And in this condition, since n is simply connected, what we have is that these two paths, gamma and alpha hat, are homotopic relative to 0, 1. In particular, because of our proof, that implies that the invariant associated to these paths is the same, right? But this is not true because this invariant was 1 and this invariant was 0. And these two classes are not the same. So we get a contradiction. Okay. And as a consequence of the contradiction, our hypothesis, the hypothesis that led to the contradiction is that actually x0 and x1 belong to the same connected component of n minus m. That's what allowed us to build this alpha, then construct alpha hat, and finally proving that 0 equal 1. So there are two connected components in n minus m. So let us see now a consequence, a corollary of the previous theorem. Let M be a compact non-orientable manifold of dimension n. This manifold cannot be embedded in a simply connected manifold n of dimension n plus 1. In particular, the projective space of dimension 2n, which is non-orientable, cannot be embedded in R2n plus 1 because the latter manifold is simply connected. So let us prove this result. Suppose that we can embed M in N. Okay, indeed, we can suppose that M is connected. There exists one of the M0, a connected component of N that is non-orientable. Okay, because if all the connected components, the finitely many connected components are orientable, then M is orientable. So up to replace M with M0, we can suppose that M is connected, okay? But now we have that a compact connected submanifold of a simply connected manifold of, indeed, a compact connected submanifold of codimension 1 of a simply connected manifold separates the ambient manifold, okay, because of the previous theorem. So the previous theorem implies that M separates N. But now, if M separates N, and indeed N is simply connected, we have that M is orientable. That's another of the theorems that we already proved. And this is a contradiction because M, by hypothesis, is non-orientable. So we get a contradiction, and this completes the proof. In this lecture, we studied some geometric applications of orientability by using as ingredients some of the techniques that were introduced previously in the course, as for instance, the density of C-infinity maps in the set of continuous maps, or the open and dense nature of transversality. Indeed, these ideas are going to be used extensively when we study later on the properties of the degree of a differentiable map between manifolds of the same dimension, or the properties of the intersection of submanifolds. But before getting there, we need to introduce a new concept, the concept of a tubular neighborhood of submanifold of an ambient space. And that's going to be the subject of our next lecture. Thank you for your attention.